Welcome to this explainer. Today, we're going on a truly fascinating journey. We're going to trace an invisible architectural thread that runs right through the absolute core of our digital world. We're looking at a story that begins with the really rigid physical constraints of 1960s computing, and somehow, incredibly, leads directly to the architecture of modern artificial intelligence. It's the story of how a brilliantly elegant solution to a massive internet problem fundamentally shaped the web, and how those exact same design decisions are impacting the most advanced large language models we're using right now.
So, I want you to keep a massive question in the back of your mind as we go through this. How does an ingenious mathematical hack, designed to fix a global internet crisis, now dictate the intelligence of modern AI? Because, what might just seem like dry computer history at first glance is actually the hidden geometry of the modern digital mind. Literally every single time you type a prompt into tools like ChatGPT or Claude, you are interacting directly with the legacy of this exact mathematical hack.
Part 1. The 7-bit telegraph origins. To really understand how we got here, we've got to rewind all the way back to the beginning, looking at the mechanical limitations of early tech.
Picture the early 1960s. A committee establishes the American Standard Code for Information Interchange, which you probably know as ASCII, and they gave it a very strict limit of just 128 characters. Now, why so few? Well, because it ran on a 7-bit system. They deliberately chose 7 bits instead of 8 because back in those days, every single bit transmitted over noisy, unreliable telegraph and telephone lines cost precious money and time. So it wasn't just a random design choice. It was a rigid financial constraint. But, it was an elegant compromise for the era, giving them just enough room for the English alphabet, numbers, a little punctuation, and a handful of control codes.
Now contrast that tiny 128-character box from the 1960s with today's Unicode standard. Right now, our digital world houses over 120,000 characters. We've expanded from just basic English letters to covering virtually every single human writing system on the entire planet. Plus, thousands of emojis, so you can always send the perfect slice of pizza or dancing alien in your group chats. But getting from that initial 128 to over 120,000 was anything but a smooth ride.
Let's trace how this actually played out. We start in 1963 with our 7-bit American standard, but as computers exploded globally in the 1980s, we hit a massive wall, which led to a highly fragmented era known as extended ASCII. Fast forward to 1991, and the computer science world realized it needed a total reset, so they introduced Unicode. And finally, by 2008, the encoding format known as UTF-8 officially took over the web, unifying our digital text forever. So what exactly happened in the 80s to force such a massive paradigm shift?
That brings us to part 2, the digital Tower of Babel. Because as personal computers went global, that original 128-character limit turned into an absolute crisis.
Engineers were desperate. They tried to fix the limitation by slapping on an 8th bit, creating what was called extended ASCII. That bumped the character limit up to 256. But here was the catch. Every region around the world used those extra 128 slots for their own local alphabets. So, if a text file was created on a Russian computer, it would look like complete and utter gibberish when opened on a French computer. It's a phenomenon called mojubake, where text just turns into corrupted nonsense. You literally couldn't even put 2 different languages in the same document. International digital communication was just fundamentally broken.
Part 3. Uncoupling character from code. To fix this global fragmentation and save the internet, the computer science world needed a complete philosophical shift.
The crucial turning point was when Unicode finally broke that old telegraph assumption that a character must equal a fixed, rigid set of bits. Instead, they cleverly split the concept in 2. First, they gave every single character in the world an abstract identity number, which they called a code point. Second, they created an encoding form, which is just the set of rules for how the machine physically stores that number in binary bits. Think of a code point kind of like a person's social security number. It's an abstract identity. The encoding form is the physical plastic ID card that actually stores it. They successfully separated the abstract idea of a letter from its physical storage.
Part 4. The UTF-8 magic trick. But here's where we run into a multi-billion-dollar problem. How on earth do you transmit this massive new Unicode directory of over 100,000 characters without breaking the entire internet?
You couldn't just force everybody to upgrade their physical hardware to a 16-bit or 32-bit system. Global infrastructure would have literally collapsed overnight. The answer was the UTF-8 transformation format. Instead of the legacy method that used really rigid, fixed-length bytes, which is exactly what caused that global incompatibility we just talked about, UTF-8 introduced dynamic, variable-length elasticity.
It just magically scales on the fly depending on exactly what character you're trying to type.
The math that makes this elasticity possible is absolutely brilliant. UTF-8 dynamically allocates just 1 byte for English, 2 bytes for Arabic or Cyrillic, 3 for Asian scripts, and up to 4 bytes for emojis. But the absolute genius lies in that first byte. For English characters, the underlying binary always starts with a leading 0. That 0 acts as a secret passcode to guarantee backward compatibility with 1960s 7-bit ASCII. The system basically reads that 0 and says, okay, treat this exactly like an old-school ASCII character. And because of this incredibly elegant engineering hack, a UTF-8 file containing only ASCII characters is, bit for bit, totally identical to an old ASCII file. Legacy servers, outdated email routers, ancient software, they could all process UTF-8 perfectly without needing a single software update. It was a completely seamless transition that most internet users never even noticed. This masterpiece of digital diplomacy is exactly why UTF-8 was able to silently take over 98.9% of the web.
Which brings us to part 5, Encoding the AI Era. Now, you might be wondering, why does a deep dive into 1990s text formatting matter so much today?
It matters because it reveals exactly why these specific byte structures are the foundational architecture of today's large language models. Modern AI tokenization uses something called byte-level byte pair encoding, or BPE. Instead of trying to learn millions of whole human words, the AI digests the internet using UTF's raw bytes as its base alphabet. Its base vocabulary is exactly 256 byte values. The AI looks for statistical patterns in those 256 bytes and groups them together into what we call tokens. Because every single text, language, and emoji can be mathematically broken down into UTF bytes, the AI is guaranteed to never encounter an unknown character. It can universally ingest any string of human text without crashing.
However, there is a hidden cost to this dynamic scaling, and it's known as byte fallback fragmentation. Because the AI processes text byte by byte, and because UTF-8 dynamically stacked its byte lengths to be compatible with English ASCII, we have a baked-in imbalance. English is 1 byte, but Arabic is 2, and rare scripts take up to 4. This means developers and users operating in non-Latin languages literally pay higher compute costs and experience slower AI generation speeds, all because of a standard established in the 1960s. An AI model literally has to work harder, read more bytes, and use way more memory just to process Hindi or Arabic compared to English.
So I'm going to leave you to chew on this fascinating paradox. Is it an absolute engineering miracle that a 1960s telegraph bandwidth constraint was so elegantly hacked that it now flawlessly governs the intelligence of modern AI? Or is this deep-rooted bias toward English ASCII actually our greatest, most invisible technical debt? Thank you so much for exploring the hidden architecture of our digital world with me today on this explainer. Catch you on the next one.